Hello everyone, myself Dr. Rajesh Baligar, working as an assistant professor in the Department of Chemistry, JSS Arts, Science and Commerce College, Gokak, which is affiliated to Rani Chennamma University, Belagavi. In the last few videos, I have discussed about the crystal field theory with reference to octahedral, tetrahedral and square planar complexes. So that means how the 5D orbitals are going to split into different sets of orbitals with different energies if the ligand environment around the center metal ion is octahedral, tetrahedral and square planar. In case of octahedral complexes, the 5D orbitals are going to split into T2Z and EG orbital. T2Z orbital consists of three orbitals, that is a dxy, dyz and dxz orbital. EG orbital consists of dx1 minus y square and dz square orbital in case of octahedral complex. That means similarly, according to crystal field theory, in case of tetrahedral complex, these 5D orbitals are going to split into EZ and T2Z set orbital. Okay. Similarly, in case of square planar complexes, these orbitals are going to split into dx square minus y square, okay, and dxy, dz square, dxz and dyz. Now already we have seen these splitting in the previous videos. In this video, I will discuss about the crystal field theory with reference to distorted octahedral structure. In the syllabus, they have also mentioned Jahn-Teller distortion. That means when a Jahn-Teller distortion takes place in octahedral complexes, in that condition, how the 5D orbitals are going to split into different sets of orbitals having different energy. That is the meaning of the crystal field theory with reference to distorted octahedral complex. Now the question comes, what do you mean by distorted octahedral complexes? Or how come this distorted octahedral differs from the perfect octahedral complex or regular octahedral complex? So in order to know that one, let us consider one hypothetical complex, that is molecule Ml6. If you draw its octahedral structure, it consists of 6 bonds, and these 6 bonds are classified into two types. One is axial bond, which can be denoted as A, and another one is equatorial bond, which is denoted by E. And the ligands associated with axial bonds are generally considered as axial ligands, whereas the ligands associated with equatorial bonds are known as equatorial ligands. Now, this is the octahedral structure of Ml6, that is hypothetical molecule. Now, if you want to call this one as a regular octahedral or perfect octahedral complex, the condition is all the bond lengths should be same. That means the equatorial bond and the equatorial bonds and the axial bond length should be same. That means in any octahedral complex, if all the bond lengths or if all the 6 bonds are having same length, then that octahedral complex is considered as a regular octahedron or regular octahedral complex. So that means all the bond lengths are same. That means axial bond length is exactly equal to equatorial bond. All the 6 bond lengths are same. If that is the case, in that case only we can call that one as a regular octahedral structure or regular octahedron structure or perfect octahedral structure. Now the question comes, what do you mean by distorted octahedral structure? Because already we know crystal field theory with reference to perfect octahedral structure. The 5D orbitals are going to split into T2Z and EZ orbital. Now the question comes, if it is a distorted octahedral structure, then how the 5D orbitals are going to split into different sets. So before going to that one, let us know what do you mean by this distorted octahedral structure. Okay. So in order to realize that one, let us start with the meaning of a distortion. The distortion means change in shape. So that means octahedral structure will be there, but only the shape of the molecule will be little bit changed. So that is the meaning of the distortion. Okay. Generally, it has been observed that in case of octahedral complexes, 2 types of distortion will take place. That means there is 2 possibility. 2 types of distortion will take place. In perfect octahedral complex, all the 6 bond lengths are same. But in distorted octahedral complexes, there is a change in the bond length. That means all the 6 bonds are of the same size. Okay. So generally, two types of distortion will take place in octahedral complex. One is elongation will takes place along the z-axis, or compression may takes place along the z-axis. In these two cases, we cannot call that octahedral structure as a regular octahedral structure or regular octahedron structure, because the bond lengths will be different from other bonds. Okay, so if elongation takes place, for example, if you consider, let us consider this one octahedral structure here. So if it is a central metal ion, let us consider one Ml6, that is hypothetical molecule Ml6 octahedral structure. If it is a octahedral structure, that is a central metal ion, ligand 1, 2, 3, 4, 5 and 6. 6 ligands are there. If it is a perfect octahedral structure or regular octahedral structure, then equatorial bond length will be exactly equal to the axial ligand length. That means all the 6 bonds are of same length. Now, in any complex, if elongation takes place, that means Z-out distortion will take place. There are two types of distortion. One is known as elongation, another one is compression. This elongation distortion is also known as Z-out distortion. That means in octahedral complex, if Z-out distortion takes place, definitely there will be 2 long bonds and 4 short bonds. Let us see that one. From this one, if it undergoes Z-out distortion, means the ligands which are present along the z-axis, that means ligand 6 and ligand 5, they are a little bit away from the central metal ion. So that means the distance between the ligand 5 and ligand 6 when compared to the with respect to central metal ion is more or is greater when compared to the distance between the other 4 bonds. So that means in case of Z-out distortion, the 2 trans ligands which are present along the z-axis, their length will be more. That means the ligands are a little bit away from the central metal ion. That means the distance is more. The distance between the central metal ion and the ligand is more when compared to the ligand which is present in equatorial ligand here. So this length will be more. So therefore, what will happen in such cases, equatorial bond length is more, axial bond length is more when compared to equatorial bond. So such type of structure will occur only when Z-out distortion takes place. So that means in Z-out distortion, the resulting complex will be definitely contains 2 long bonds. That means these 2 elongated bonds. That means 2 long bonds and 4 short bonds. This is also known as elongated tetragonal structure. Z-out distortion structure is also known as elongated tetragonal structure because it is octahedral complex only. The elongation will take place along the z-axis. These 2 ligands will little bit away from the central metal ion when compared to other 4 ligands which are present in xy plane or in equatorial position. Okay, so this is also known as elongation Jahn-Teller distortion, that I will explain later on. Okay, similarly another one distortion will take place, that is compression. So that means if it is a perfect octahedral complex, if the 2 ligands which are present along the z-axis, if they are more nearer to the central metal ion, if these ligands, for example this 5 and 6 ligands, if they come more nearer to the central metal ion, then the distance between this ligand and the central metal ion is less when compared to other 4 ligands which are present in xy plane. So in such cases, Z-in distortion takes place. That means whenever Z-in distortion takes place in such complexes, 2 short bonds will be present and 4 long bonds will be present. Okay, whenever Z-in distortion takes place, the compression will take place, which is also known as compressed tetragonal structure. Okay, in compressed tetragonal structure, what will happen? The ligands which are present along the z-axis are more nearer to the central metal ion when compared to other 4 ligands which are present in xy plane. So as a result of this one, 2 short bonds will be formed and 4 long bonds will be formed here. This is also known as compressed Jahn-Teller distortion. And these two distortions, that means Z out distortion and Z in distortion, are commonly known as tetragonally distorted octahedron structure, because it is octahedron structure only, but distortion may take place in a two pattern. One pattern is elongation may take place along the Z axis, or compression may take place along the Z axis. If elongation takes place, that is known as Z out distortion, okay, and if compression takes place in, that is known as Z in distortion. In case of elongation distortion, two long bonds will be there. In case of Z in distortion, two short bonds will be there. So these two common distortions are commonly considered, or it is known as tetragonally distorted octahedron structure. Now the question comes, why the distortion will take place? Why we are not getting perfect octahedral structure or regular octahedral structure or regular octahedron always? So that fact is explained by the two scientists. First, in Hermann Jahn and Edward Teller in 1937, they have proposed their theory in order to explain why and how or in what condition the distortion will take place in octahedral complex. According to them, in any nonlinear molecule, if degenerate d orbitals are asymmetrically occupied by electrons, then definitely distortion will take place to remove the degeneracy. Okay, that means according to Jahn-Teller's distortion. Okay, if they may ask you to write the statement of Jahn-Teller distortion or explain Jahn-Teller distortion. Okay, so in that condition we have to write, in any nonlinear molecule, if degenerate orbitals are asymmetrically occupied by electrons, a distortion will take place to remove the degeneracy, or stability and degeneracy are not possible simultaneously unless the molecule is linear one in regards to electronic state. This leads to break in degeneracy, which stabilizes the molecule and by consequences reduces its symmetry. Okay, so this fact I will explain later on also. Okay, in later on I will explain in detail about the Jahn-Teller distortion. Okay, in what condition the Jahn-Teller distortion takes place, what are the conditions for the strong Jahn-Teller distortion, what are the conditions for the weak Jahn-Teller distortion. So that I will explain later on. But before that one, we know that two types of distortion will take place, and in these two types of distortion, how the 5d orbits are going to split into different sets of orbits, that we have to see first. So let us study one by one. So that means crystal pill splitting in case of Z out distortion case and crystal pill splitting in case of Z in distortion case. So let us study the crystal pill theory with reference to elongated tetragonal structure. That means crystal pill splitting in case of elongated tetragonal structure. That means when the Z out distortion takes place in octahedral complex, in that condition how the 5d orbitals are going to split into different sets of orbitals having different energy. Let us see that one. So we know that in Z out distorted octahedral complex, there are two long bonds and two short bonds. In Z out distorted octahedral complexes, the two trans ligands which are located along the Z axis are little bit away from the center metal ion when compared to the other four ligands. So that means the distance between the Z axis ligands is greater, or it is more when compared to the ligands present in the XY plane. Okay. As a result of this one, the two long bonds and four short bond structure will be formed. Okay. Here therefore the d orbital lobes. Now if this is the situation, that means in a elongated tetragonal structure, what will happen? The two bond lengths are more when compared to the other four bond lengths. Here the ligands which are present along the Z axis, the bond length is more when compared to the ligand present in the XY plane. So therefore the ligands which are coming along the Z axis are a little bit away from the center metal ion. The distance is more. So as a result of this one, what will happen? The d orbital lobes which are present in the z axis, or the d orbitals whose lobes are present in z axis, or d orbital lobes with z component or z plane, will experience less repulsion, because what will happen? See, the center metal ion consists of 5 d orbitals, dxy, dyz and dxz and dx square minus y square and dz square. Okay, so that is according to crystal field theory, it is considered as a positive ion of charge equal to its oxidation state. Similarly, the ligand is also considered as a point charges. In general, we are going to consider as a negative field. So if the ligand is a little bit, the ligand distance is more, so the gap is more. Okay, if gap is more, of course the electrostatic force of attraction will take place between the center metal ion and the ligand, but at the same time the electrons which are present in the d orbitals of the center metal ion will experience less repulsion from this negative field. So as a result of this one, the d orbitals whose lobes are present in z axis, or the d orbital lobes with z component, will experience less repulsion when compared to the d orbital lobes which are present in xy plane. Now the question comes, what are those d orbitals whose lobes are present in z axis, or whose lobes are containing z component? So out of 5 d orbitals, that is dxy, dyz, dxz, dx square minus y square and dz square, this is T2G set and it is EG set in case of octahedral complex. Okay, now out of the 5 d orbitals, let us see which orbital lobes are present in z axis, or which orbital lobe contains z component. Here from the T2G set, dyz, z component is there, dxz, z component is there, dyz and dxz. Now from the EG set, the dz square orbital will also come along z axis, that is it also contains z component, and another orbitals, then the other orbitals contains, or they are present in xy plane. Now since in elongated tetragonal structure the z axis ligands are a little bit away from the center metal ion, they will experience less repulsion. Therefore, if less repulsion is there, their energy decreases when compared to other 4 ligands, because when compared to other 4 ligands, these ligands are little bit away from the center metal ion. Therefore, the equatorial ligands will experience, or the equatorial ligand, the orbitals which are present in xy plane will experience more repulsion when compared to the orbital lobes which are present in the z component. So that means here out of these 5 d orbitals, the dz square, dxy and dyz orbitals will be having lower energy, because they will experience less repulsion, lower energy. At the same time, the orbital lobes which are present in xy plane, that means dx square minus y square and dxy orbital energy increases. Now in order to write the crystal field splitting diagram for elongated tetragonal structure, that means elongated octahedral structure, so we have to first write the crystal field splitting diagram in case of regular octahedral structure. From that only we can derive the crystal field splitting for the elongated tetragonal structure. So this is the crystal field splitting diagram for the regular octahedral structure or regular octahedral complex. The 5 d orbitals are in free metal ion and average energy of 5 d orbitals in spherical field, and in case of octahedral field, the 5 d orbitals are going to split into T2G and EG orbital. T2G orbital consists of dxy, dyz and dxz orbital, whereas EG orbital consists of dx square minus y square and dz square orbital. Now from the discussion, it is very clear that the z axis components orbitals, that means dx square minus y square orbital and dxz and dyz orbital energy decreases, whereas dx square minus y square and dxy orbital energy increases. That we have to show in this diagram. Here dx square minus y square, if it is present in EG orbital, therefore I will write here this is dx square minus y square, and at the same time dz square orbital energy is less. So right here. Okay. Similarly, from the T2 set, which orbital energy decreases and which orbital energy increases here? Okay. So dxz and dyz, dxz and dyz orbital energy decreases. Okay. Similarly, dxy orbital energy increases. You write this one here. Okay. So this is the crystal field splitting diagram for elongated tetragonal structure. That means in elongated octahedral structure, how the 5d orbitals are going to split? They are going to split into dx square minus y square, dz square, dxy and dxz and dyz orbital. Here the energy difference between dx square minus y square and dz square, it is represented by delta 1 and it is denoted by delta 2. Okay. Here always the delta naught value, always delta naught value is greater than delta 1, which in turn is greater than delta 2. Okay. So this is how we are going to write the crystal field splitting diagram for the distorted octahedral structure. That means when the Z out distortion takes place, this is the crystal field splitting pattern. So let us see another one is, that means a compressed tetragonal structure, how the crystal field splitting will take place. Let us see that one. Now let us study the crystal field splitting in case of a compressed tetragonal structure, that is a compressed octahedral structure or octahedral structure in which Z-in distortion is taking place. In such complexes, what will happen? The transligands, the two transligands which are located along the Z-axis will come more nearer to the centrometal ion. That means the distance between the Z-axis ligand and the centrometal ion is less when compared to the distance between the centrometal ion and the ligands which are present in xy plane is very less. So therefore, as a result of this one, what will happen in a Z-in distortion? That means any octahedral complex, if it is suffering from the Z-in distortion, in such structure, definitely there will be presence of 2 short bonds and 4 long bonds. Okay, these 2 short bonds are because of the presence of the or coming of the Z-axis ligand more nearer to the centrometal ion when compared to the other 4 ligands which are present in the xy plane. So as a result of this one, what will happen? The d orbital lobes which are present in Z-axis or the d orbital lobes containing Z component will experience more repulsion because the ligand is more nearer to the centrometal ion. The Z-axis ligands are more nearer to the centrometal ion here. So as a result of this one, the centrometal ion already it contains 5 d orbitals. Okay, the d orbital lobes which are present in Z-axis or which contains Z component will experience more repulsion because the distance is less when compared to the other other orbitals which are present in xy plane. So as a result of this one, what will happen? The dz square, dxy and dyz orbital will experience more repulsion. Hence, if more repulsion is there, then more energy. Similarly, when compared to the Z-axis ligands, the xy plane ligands are a little bit away from the centrometal ion. That means the distance is more when compared to the distance between the centrometal ion and the Z-axis ligand. Therefore, the orbitals whose lobes are present in the xy plane will experience less repulsion. So as a result of this one, what will happen? The orbitals lobes which are present in xy plane will experience less repulsion, hence their energy decreases. So here dx square minus y square and dxy orbital energy decreases. That means less energy. So this fact can be represented in crystal field splitting diagram as shown in this figure. Okay, so in order to show this fact, we have to first consider the crystal field splitting diagram in case of regular octahedral complex, because from the regular octahedral complex only, if Z-in distortion takes place, such type of complex will form where 2 short bonds and 4 long bonds are formed. So this can be represented by taking the octahedral crystal field splitting diagram. So in octahedral crystal field splitting diagram, that too regular octahedral crystal field splitting diagram, the 5 d orbitals are going to split into T2z and EZ. T2z orbitals consists of dxy, dyz and dxz orbital. Similarly, EZ orbital consists of dx square minus y square and dz square orbital. Now from the structure and the discussion, it is very clear that the z-axis component orbitals will be having more energy. So that means we have to show like this one. Which one is having more energy here? Z square, dz square orbital will be having more energy because they are more nearer to the center metal ion, more repulsion will take place, more energy. Therefore, this was dz square, and similarly dx square minus y square will be having less energy. So show this one here. From the T2G set, dxz and dyz orbital will be having higher energy, dxz, dyz, and in Z-in distortion case, dxy will be having lower energy. So again, the energy difference between the dz square and dx square minus y square is denoted by delta 1, and the energy difference between dxz, dyz and dxy orbital is delta 2. So generally we are going to consider the energy difference between dx square minus y square and dxy is delta naught. Okay, here always delta naught value is greater than delta 1, and which in turn is greater than delta 2. Okay, so this is the crystal field splitting diagram for compressed octahedral structure or octahedral structure which is suffering from the Z-in distortion. In such cases, what will happen? It will split into, the 5 d orbitals are going to split into dz square, dx square minus y square, dxz, dyz and dxy orbital. Okay, this is how the crystal field splitting diagram can be explained for either elongated or compressed tetragonal structure by crystal field theory. Okay, thank you.